Hi friends, very good morning and welcome to the Ignite classes. Today we are going to learn an interesting topic that's on Lorentz force. We can learn this topic in this fourth chapter of NCRT, that is moving charges and magnetism. Okay, so let us start. So what's this Lorentz force? That's what we have to learn. Okay, so in a region we have electric field. So I am indicating this electric field in this blue color arrows, okay, and representing this magnetic field with cross because it's directed inward. So I am indicating its Y cross sign, okay. So we have this magnetic field as well as what? As well as this electric field perpendicular to each other. Okay, to this region, what comes? A charge q enters to this region, okay, with a velocity v, okay. Then, what are the forces experienced by this charge? That's a question. Here we have electric field, then magnetic field. When a charge q with velocity v enters this region, what are the forces experienced by this charge? Definitely, we know that there will be electric force. Okay, there will be electric force as well as magnetic force. Okay, so both this electric force as well as magnetic force acts on this charge simultaneously because to this region where it is going to enter, both electric field and magnetic field are present. Both are present there, so they act simultaneously. Then what will be the sum of this electric field, sum of this force, electric force, as well as this magnetic force? It will be Lorentz force. Okay, so this is nothing but Lorentz force. So basically, Lorentz force is the sum of electric force and magnetic force acting on a charge q when it is entering the region where E and B, electric field and magnetic field B, are present, okay, with a velocity, and it is entering with a velocity v. Is it clear for you? Okay, so Lorentz force, that is equal to electric force plus magnetic force. So what's the force experienced by a charge q in an electric field? That is F electric, that is equal to F electric, that is equal to what? Q into E. Q into E, where Q is the charge, where it is a scalar quantity, and E is the vector quantity, Q into E. Suppose this charge is now, it is at a location R. Okay, so we can write it as this E as a function of R, Q into E of R. Then what will be this magnetic force? That's a question. Okay, that we have to find. So I'm doing the case of this magnetic force separately. That is, we have this magnetic force, magnetic field. Now we have to find this magnetic force. Okay, so magnetic field directed inward is here. Okay, and the charge q is entering to that magnetic field with a velocity v. Definitely this direction of this velocity, it is perpendicular to that of the direction of this magnetic field. Okay, then this Lorentz force, we know it is a sum of electric force and magnetic force. Here what we are determining, we are finding out the magnetic force. Magnetic force is equal to q into V cross B. So what is this cross product? V cross B. Here we have V vector and B vector, and we are finding its cross product. So definitely the cross product of V vector and B vector, that would be the one which is perpendicular to both V and B. Okay, V cross B means magnitude of V into magnitude of B into sine of the angle between the two. Okay, so that's the meaning of this cross product. So Q into V cross B, magnetic force equal to Q into V cross B. So we know that Lorentz force, it is the sum of this electric force as well as the magnetic force. So it will be Q into E of R plus Q into V cross B. Okay, is it clear? Okay, then. So I'm writing what's Lorentz force for you. Lorentz force, that is equal to Q E of R plus Q into V cross B. So taking this Q as common, F equal to, taking Q outside, Q into E of R plus V cross B. Okay, this is nothing but the Lorentz force. Okay, then suppose only magnetic field is present at that region. We remove this electric field. Then what will be the Lorentz force? Then Lorentz force, it gets reduced to magnetic force Q into V cross B. Okay. Then a charge Q, it is entering to that magnetic field, and this magnetic field, suppose it is uniform, it's a uniform magnetic field, and to this field this charge Q that's entering with a velocity V. Okay, now we can find what? We can find that this charge performs circular motion inside this magnetic field. So, in order to maintain that circular motion, this magnetic force, what's the magnetic force? That is F a magnetic, that is equal to Q into V cross B. This magnetic force provides the centripetal force required for that circular motion. One more time. Then, when this charge Q enters this region having only magnetic field, having uniform magnetic field, then this charge Q will perform circular motion inside this magnetic field. Okay, so we have to find the radius of that circle. Okay, since it is having that circular motion, we have to find that radius. Okay, so we know that the equation for the centripetal force, I'm representing centripetal force by this Fc, that is equal to mv square by r, where m is the mass of the particle, v is the velocity, and r the radius. Then magnetic force, we know it is q into v cross b. Here V is perpendicular to V vector, it is perpendicular to B vector. Okay, so it is Q into V, magnitude of V, we can write it as V, then B, magnitude of B, that is B, then sine 90. Sine 90, we know that its value is 1, so it is equal to QVB. We know that the centripetal force is provided by magnetic force, that is they are equal in this case. So Fc, that is equal to F magnetic, that is magnetic force, that is mv square by r equal to q into vb. We can cut one v on both sides, then what remain? Mv by r, that is equal to qb. Taking r to this right side, we get what? mv by qb. So r, that is the radius of that circle, that is equal to mv by qb. It's very important equation from this section because so many questions were asked from these sections, from this using this equation in so many competitive examinations. So this equation, it's that much important, and please remember this equation. Okay, then so we cover this Lorentz force. What's this Lorentz force we learn? So basically, to a region having both magnetic field as well as electric field, a charge is entering. Okay, charge is entering with what? With a velocity. It's not stationary. It's entering with a velocity v, and this E and B are mutually perpendicular, as well as this velocity, it's perpendicular to magnetic field. Then Lorentz force, it's the sum of this electric force as well as this magnetic force experienced by that charge entering that field. Okay, so the equation to find this Lorentz force, that is equal to F equal to Q into E of R plus V cross B. This is the equation to find this Lorentz force. And if there is no electric field, then only Q into V cross B. The Lorentz force gets reduced to Q into V cross B. Okay. And one more thing you should note, that this magnetic force, we have this magnetic force that is equal to Q into V cross B. Okay, that is, this magnetic force is perpendicular to V as well as B. Since it is the cross product of V and B, magnetic force is perpendicular to V and B. Now, when we are calculating this work done using this work will be magnetic force into displacement. We know what? Velocity equal to displacement by time. So that is displacement equal to velocity into time. Okay. So F magnetic into velocity, here cross product into velocity into time. We know that F magnetic, that is magnetic force, is perpendicular to this velocity. So their cross product will be F magnetic into V into sine. Not, we have to find, yes, this is work, so this is cross product. Okay, it's not cross product, it's dot product. Okay, sorry. So this is dot product. So in that case, what we should do, the definition of W, that is work, is force into displacement. That is, there we are taking dot product. So don't put cross there, because that cross, we use this cross mark to indicate this cross product in higher classes, but in lower classes you use this into marks just for multiplication. So don't get confused, just put this dot. So dot product means we are finding this magnitude of this force into magnitude of this velocity into cos of the angle, that is equal to 90. Cos 90, that is 0. So this becomes 0. So work done by this magnetic force is 0. Okay, it's 0 always. So it's one more thing that you should remember. So then what we learned? We learned this, that when there is only magnetic field, uniform magnetic field present, and when this charge q enters to that region with velocity v, it will perform circular motion, and the radius of that circle is equal to mv by qb. Very important equation. So just remember this equation always, because it's a sure question for competitive exams. Okay, so now we can move on to a problem based on this Lorentz force. It's a textual problem, simple but uh, much important. Okay, so this is that problem. A straight wire of mass 200 gram, mass that is equal to 200 gram, mass equal to 200, and length 1.5 meter, carries a current of 2 ampere. It is suspended in mid-air by a uniform horizontal magnetic field B. What is the magnitude of that magnetic field? That's a question. So straight wire of mass 200 gram. So we can write it. Mass it is 200 gram. Mass equal to 200 gram. Okay. Length equal to what? Length equal to 1 minute. Yes. Length that is equal to 1.5. Okay. 1.5 meter it is. Then carries a current of 2 ampere. So length 1.5 meter and current that is 2 ampere. So we can write it length equal to 1.5 meter, 1.5 meter and current that is equal to 2 ampere. Okay. So it is given that this wire it is suspended in air. Okay. This wire that is suspended in air, they had given that. Okay. So we have to find that magnetic field. Since it is suspended in air, with what? With this, yes, with this force. So we have one equation, that is force. This force on this wire that is equal to F equal to ILB. We have F equal to ILB. There is an equation, and when we find it, we get mg that is equal to ILB. This gravitational force that is equal to magnetic force, and from that we can find B that is equal to mg by IL. Okay, calculating, just substitute this value of m and L and I so that we get B. Okay, here this gravitational force that is equal to magnetic force. So magnetic force on a conductor that is equal to ILB. So that's all. If you like the class, please subscribe and just mark the attendance by pressing the like button.